Welcome to Web Handling. My name is Dave Roysam. I am super excited to continue our new series called Insular Industries. Here we will highlight some of the cultural blind spots that some mega industries have in certain web handling areas. In this show, we will cover one of the oldest and largest and arguably most proficient of the web industries, paper. If they can have web handling blind spots, pretty much anyone can. I know your time is precious, so let's get started. We begin this series with paper, a truly impressive industry. First, it is one of the oldest of the web industries, about 2 centuries old. Second, it is one of the largest of the web industries, having a market value of something like $250 billion per year. Finally, it is one of the most proficient of the web industries. It almost invented rollers, motor control, web testing, and much, much more. Thus, you would think that these guys would have it all figured out. But no, they have missed some truly basic web handling technologies that are known by tens of thousands of people who work in other industries. Let me illustrate with just a few examples. One of the many glaring culture blind spots of the paper industry is the entire area of web path control, otherwise known as guiding. As a point of reference, most industries can hold the position to better than a few hair's thicknesses. They use theoretically sound and field-tested guide geometries, such as given on this list. We need not detail how to do that because path control and guides is covered in chapter-length detail in the must-have 750-page Web Handling Handbook. It is also covered in my award-winning and trademark Web 101 class that has been taken by about 5,000 students. In any case, the paper industry is lucky if they can control felt and wire positions to within a few centimeters. Worse yet, crashes and destructions of $100,000 felt and wires is common due to poor guide mechanicals and poor guide controls. The major reason for this poor performance is that, to my knowledge, not a single builder has ever used those above theoretically sound and field-tested geometries. Instead, they tinker with geometry after geometry that a web handler could tell them at a glance will not work well, or not at all. So, let me justify my scathing critique with a concrete example. In review, there are 2 major considerations for effective guides: wrap angle and span length. The wrap angle on the guide roll should be close to 90 degrees. The span length depends on a number of factors detailed elsewhere, but mostly upon which type of guide is being used. The steering guide requires much longer paths than the displacement guide. The reason, my students will recall, is the severity differences between in-plane bending and out-of-plane twisting roller misalignments. Now, we will take one of the most common wet-end guides on a paper machine wire. There have been approximately 1,000 machines made very much like this. Here, the guide roll is not wrapped 90 degrees, and the span length is inadequate. Finally, traction may be marginal due to the lubricating effects of water. While this is but a single example, it is illustrative of the thousands of wire and felt guides on the wet ends of paper machines. True, these so-called guides often move the web good enough to keep it on the rollers. However, often is not good enough and merely keeping it on the rollers is not an impressive performance benchmark. Next, let us move to the other end of the paper mill and look at the two-drum winder, of which there have been thousands built along very similar geometries. This machine I'm quite familiar with because I designed them, and I was later a manager of winding research for that machine. Specifically, we will consider the so-called guide roll. I say so-called because that roller does not guide at all, as detailed in the previous references. Instead, it is better termed a skewing roller because it is used like other skewing rolls elsewhere, as found in the front of some coating heads and most printing decks. What that roller really does, quite crudely, is to compensate for the linear portion of bagginess profile, sometimes called camber. It will not help with baggy edges, baggy center, or a baggy lane. Only limited help with the camber portion of bagginess profile. When I say crudely, I mean that the vertical movement of the roller is adjusted with a large hand wheel without any feedback such as roller position or web tension. What is most striking to the web handler is the inconsistency of alignment standards. On every one of the other dozen rollers on that machine, the standard alignment as given by most of the builders is 0.02 of an inch per 100 inches, or 0.05 of an inch total, the thickness of a human hair. Yet, incredibly, the allowable misalignment travel of this specific roller is 2 inches, or 1,000 times as much as the neighboring slitter rollers or drums or unwind, for example. Why this didn't strike others in the paper industry as odd is not odd. They got used to seeing it that way for more than a century, and that became normal or standard. Yet web handlers know better. That movable roll can be made precise within a line zero, micrometer consistent mechanicals, and guided by load cell feedback. All of the major winder builders have alignment tolerances specified something like this: 0.02 of an inch per 100 inches of width and 0.05 of an inch maximum. That's the thickness of a human hair. How this standard got that way is simple. It is what could be done rather than what should be done. By that I mean that the alignment tooling and the roller mountings were good enough to easily reach those tolerances on most occasions. Yet there are 2 hints that this one-size-fits-all is a bit hinky. The first is the 2-inch guide roll travel, as we just discussed. The second is the 2-inch bow that might be found on some bowed rollers. Yes, the edges of the bowed roller are indeed misaligned, just like every guide roller ever built. Thus it is clear that paper can take more, much more, at least in many cases. However, while a hair's thickness tolerance may be too tight for some places, there are places where fractional hair width errors are way too much. The first is the boundaries between 2 segmented roller segments. Here, even 0.001 of an inch error can cause shear wrinkling because the basis is not the width of the machine or even the 20-inch segment. Rather, it is the gap width, which is 100 times shorter than the roller itself. Another example of hair's thickness tolerances being too loose is detailed elsewhere, but it is roller wear in a narrow band, especially on thin materials. Of all of the industries, the paper mill is most awash in data. Data from perhaps as many as 10,000 sensors might be gathered and stored in some of the larger pulp and paper complexes. Yet, as with all industries, customer complaint data is a bit hinky. Specifically, we will give the example of web break reporting data, though almost all data coming from the customers is suspect, as I have covered in other clips. Web break reporting on newsprint and sometimes magazine grades are reported in printing press breaks per 100 rolls. Typically, the break rate is a few percent. Yet, to be statistically sound, the sample size needs to be in the thousands. Seth and Page, way back in the 1970s, is that environmental conditions at the customer has a larger effect on web breaks than does the paper itself. Other factors bigger than the paper quality include printing press design, printing press maintenance, and printing press operation. Thus, web break rates that they post every week is no more meaningful and trustworthy than random numbers. One final specific example that many other industries share is the misunderstanding of what roller grooving does and how to design it. One machine builder alone had 2,000 grooving patterns in their drawing files. There simply cannot be 2,000 different requirements on a paper machine. Still, they got one thing very, very right. That is the Beloit trademarked venta grooving that has been widely copied. That grooving can handle air to speeds well in excess of 12,000 feet per minute or 4,000 meters per minute. Web handlers now know why. It is based on the air entrainment model formulated by Knox and Sweeney way back in the 1980s. Once you know how much air is entrained, you pretty much know how to optimize grooving geometry to handle it. The details are well documented in 2 of my books and a free Abbott app. Of course, with an industry as old and big as paper is, we can find many, many other examples of cultural handicaps with respect to web handling. These include spring-mounted rollers, spreaders with insufficient pre- and post-web span lengths, draw control on the dry end of paper machine, tungsten carbide coating, and the obsession with winder TNT control curves that is also shared by most other industries. Unfortunately, we do not have time to detail those and many more in this introductory series. Thank you so very much for joining me in this Insular Industries mini-series. Please join me next week where we will continue our discussion of cultural handicaps by moving into another formidable industry, metals. If you have a topic you would like to hear about, let me know in the comments section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.